Welcome to This Explainer. Today, we're looking at something you probably remember from math class, but we are going to see it in a completely new light. We're talking about coordinate geometry. Now I know, you're probably picturing dry sets of rules or staring at boring graph paper, but honestly, scratch that. As the source material we're diving into reveals, this isn't just a rigid mathematical concept. It is an evolving, absolutely brilliant human tool that has fundamentally changed how we understand and navigate our entire world.
To really grasp the power of this tool, I want you to imagine a scenario. Pose this question to yourself. How do you map out a brand new room if you literally can't see it? It's a pretty profound challenge, right? Well, in our text, we're introduced to a visually impaired student named Rian. He and his family have just moved to a new city. And settling into a new physical space, just figuring out where the walls, the doors, and the furniture are, is a massive hurdle when you can't rely on sight.
So, to help him out, his sister, Shalini, steps in. She used her knowledge of coordinate geometry to build him a rectangular grid. She literally placed pins at the corners of objects, like his bed and his wardrobe, and connected them with thick wool. By doing this, she translated the abstract empty space of Rian's new bedroom into a physical, accessible, tactile map. She basically gave Rian a way to navigate and feel the exact layout of his room right at his fingertips.
Okay, let's dive into this, because what Shalini did for her brother on a micro level, just in a standard 12 by 10 foot bedroom, is exactly the kind of grid thinking that humanity has relied on for millennia. We use this exact same logic to map our entire reality, from the smallest rooms to our vast oceans, all the way up to charting the stars in the night sky.
You see, the concept of the grid didn't just pop out of nowhere. It's been evolving for thousands of years. It's like an intellectual baton being passed down through history. The first systematic use was actually on a massive urban scale around 3000 BCE in the Sindhu-Saraswati civilization, where they laid out city streets with incredible precision. Fast forward to 800 BCE, and the Indian mathematician Bhaujana used intersecting lines to lay the groundwork for geometry. Then that baton goes to the Greek mathematician Ptolemy around 150 BCE, over to Brahmagupta in 628 CE, all the way until René Descartes officially formalized the math in 1637. And listen, this wasn't just theoretical guys sitting around doing math for fun. This was an intensely practical tool for survival and exploration. Ancient scholars used the Indian city of Ujjaini as a prime meridian to measure the longitude of literally everywhere else. Around 499 CE, Aryabhata mapped the celestial sky by replacing Greek chords with signs, which made it way easier to pinpoint a star. Later on, the incredibly influential Arab scholar al-Biruni traveled to India, studied those exact texts, and calculated city coordinates all across Asia. He also perfected the astrolabe, a device that lets sailors navigate the open ocean just by looking at the stars. This grid system literally enabled global navigation.
But to make the modern coordinate system actually work, there is one absolutely crucial architect we have to highlight: Brahmagupta. Around 628 CE, he formally defined zero and negative numbers as true algebraic entities. And here's the thing, without Brahmagupta formalizing zero and those negatives, the modern four-quadrant system we use today, where we can measure backwards and forwards, up and down from a central starting point, that would be completely impossible.
So, how does the engine of this system actually function? Let's zoom right into the Cartesian plane. It is simply a two-dimensional space defined by two intersecting perpendicular lines. The horizontal line is what we call the x-axis, and the vertical line is the y-axis. And that crucial intersection point right dead in the middle, that is the origin, labeled mathematically as 0, 0. It's the anchor for everything.
Because those two axes intersect like a giant crosshair, they divide the entire infinite space into four distinct sections, which we call quadrants. From the origin, if you measure to the right, it's positive on the x-axis, and to the left is negative. Measuring upwards is positive on the y-axis, and downwards is negative.
Now, what's really interesting about this is how beautifully simple the rules are for plotting absolutely any point in these four quadrants. In quadrant I, the top right, both the x and y coordinates are positive. Down in the bottom left, in quadrant 3, they are both negative. This simple framework is incredibly powerful because it means you can instantly understand where something is located in a 2D space just by looking at whether its two numbers are positive or negative.
Let's connect this abstract math right back to our human story. Look at how perfectly Rian's room maps onto this exact coordinate system. By taking the bottom left corner of his bedroom and placing it right at the origin, 0, 0, the left wall naturally becomes the y-axis, and the bottom wall becomes the x-axis. Suddenly, every single corner, every door, and every piece of furniture has an exact, fixed mathematical address.
To see how these specific coordinates work in a real physical space, let's compare 2 points from his room. Point A is at 12, 0. Because the y-coordinate is 0, it sits perfectly flat on the x-axis, exactly 12 units to the right, which defines the bottom right corner of his room. Compare that to point C at 0, 10. Here, the x-coordinate is 0, so it lies squarely on the vertical y-axis, 10 units straight up from the origin, marking the top left corner.
And we don't have to stop at the bedroom. We can expand this map to the rest of the house. Notice the bathroom layout, specifically points B1 and B2 located on the y-axis. They represent the two sides of the bathroom door. By simply looking at their y-coordinates on the grid, we can easily calculate the exact width of that doorway. This proves how coordinates aren't just for plotting dots. They literally help us measure physical access, design safe spaces, and evaluate if, say, a doorway is wide enough for someone in a wheelchair to comfortably pass through.
But this brings up our next really big challenge in navigation. We know how to measure straight lines along the x or y axes. That's easy. But what if a line isn't parallel to the axes? What if Rian needs to find the absolute shortest path straight from his bed to the wardrobe, diagonally across the room? How do we measure the distance of a diagonal line between two random points?
The logic to solve this mystery is incredibly elegant. First, you find the horizontal distance between your 2 points. Next, the vertical distance. And finally, you apply the Baudiana-Pythagoras theorem. It turns out that calculating any diagonal distance is literally just using a right-angled triangle that happens to be hiding in plain sight on the grid.
And this brilliantly illustrates exactly what those steps mean. Visually, if we want to find the diagonal distance between points A and D, we just draw a horizontal line straight over from A and a vertical line straight down from D until they meet. Just like that, boom, we formed a right-angled triangle on our grid. We just measure the horizontal shift, measure the vertical shift, and use our old friend Pythagoras to find the length of that diagonal side.
This visual logic is exactly what gives us the general distance formula for coordinate geometry. To find the distance between literally any 2 points on a plane, you simply take the square root of the sum of the squared horizontal distance and the squared vertical distance. I know, it might look a bit intimidating when it's written out algebraically as x2 minus x1 squared, but visually, it is literally just finding the sides of a hidden triangle. And the real genius of this system is how incredibly robust it is. If you take that exact same triangle and reflect it across the y-axis entirely into the negative space, the coordinate signs become negative. But because we square those negative distances in our formula, they become positive again. The actual physical side lengths are perfectly preserved. The math works seamlessly, proving it's a reliable tool no matter where you are mapping on the plane. Which brings us to the profound beauty of coordinate geometry highlighted in our source material today. The incredible, world-changing power of this entire system boils down to this. Any point in a two-dimensional plane could be defined by simply 2 numbers. Just 2 numbers, an x and a y. That is all you need to define absolute location and absolute distance anywhere.
It's a mathematical framework that completely transcends scale. So I want to leave you with this final thought. If just 2 simple numbers can give a blind student a tactile map of his bedroom, lay out an ancient city grid, and chart the stars for global navigation, what unknown spaces are we going to map next? Thank you so much for joining me on this explainer, and I really hope this gives you a completely new perspective on the grids that surround us every single day. Keep mapping your world.